Okay, so that's what we're talking about. We talk about deep learning. And you may remember it, we started off with some kind of introduction. Introduction. And in the introduction, we've seen like that we have, oh wow, this is really big. Excellent. So in the introduction, we have seen that deep learning is a very interesting technology, that it's been used in many, many applications. We've seen stuff like AlphaGo. We've seen that it's used in medical image processing. We've seen that it's used in Siri and many of everyday applications. And we've also seen a couple of like high-profile applications. There was this impressive video where we looked at this James Bond movie and the object detection in it, that it actually also works on data such as that. And then, of course, not everything is solved. So there are also a couple of limitations and future directions. And in particular, we've seen that the hard tasks like image captioning, they kind of work, but sometimes it also still goes pretty crazy. So not everything is solved yet, but people are tackling now things that we thought are really, really hard to do. And they really aim at doing this. And now if you look into social media or also in the news, you can see AlphaFold, that protein folding is being tackled by this, then that people are also going into image generation from text. So very interesting approaches that are coming up there. And many people did not think that this would be possible like 10, 15 years ago. So really a lot of breakthroughs with this technology. And then we started going back to the basics. We reviewed the postulates of pattern recognition. What is a pattern? How do we recognize it? What are the basics of machine learning? And yeah, this comprises approximately what we have talked about in the introduction. So after the introduction, we went ahead, and a very important topic for us are, of course, neural networks, right? So, no, I don't want to do that. Is it? And the feed-forward networks. So feed-forward networks, we revisited the basics. And of course, everybody should know about Rosenberg's perceptron, and you should know about how this then has been evolving into like deep networks. And in particular, one important piece of theory that I really want to emphasize again at this point is the universal approximation theorem, and that the universal approximation theorem tells us that a single hidden layer neural network is enough to approximate any continuous function on a compact set. So this is kind of in contradiction to what we know from deep learning, that we have layer after layer after layer. And we've seen that the problem with this single hidden layer neural network is that if we want it to be really versatile, we have to go with the number of neurons of this layer towards infinity. And if we stack layers on top and also combine like convolutions and so in, then we are able to approximate more efficiently the underlying unknown function. So this is a key observation, that if we know something about the problem, for example, if you want to approximate trees, we had this example there, then a two-layer neural network can exactly describe this function and not only approximate it. So building deeper networks can have advantages, although the common theory, like the universal approximation, is kind of contradictory to this. And then we've seen how to actually build a feed-forward network. We looked in much detail into the backpropagation algorithm, how to train them and how to adjust the weights. And everybody should, of course, know the backpropagation algorithm, that you essentially have to know the derivative for every node in the network. You have to know the derivative with respect to the inputs and with respect to the weights. And if you know those two derivatives, then you can build a graph and compute all of the different derivatives. And this is essentially done by computing a forward pass, comparing to the target function, and then multiplying all the steps along the path until you have the respective derivative for the respective weight or wherever you want to update. And a lot of this can, of course, be reused. So this is why backpropagation is a very efficient algorithm to train these feed-forward neural networks. We looked at all of this on a node link level, and then we also learned that a fully connected layer can be represented as a matrix. And then we also seen that you can also work with matrix derivatives to compute the derivatives for entire layers at once, which allows us to reduce the complexity of the math a little bit, and it allows us to elegantly write up entire layers just with a few symbols. So that was approximately the feed-forward neural networks. How is the training done? Backpropagation, layer abstraction. So you should definitely know about these things. Then we further went ahead and we looked into the loss and optimization. Okay, I have a British English here. Okay, can we also move this guy here? So there's a couple of topics, so we move it here. So in the loss and optimization, we have seen classification and regression losses. So this is something everybody should know. So you should know about at least one classification and one regression loss. We've seen that if you start off with a Gaussian distribution, then we do formulate this as a maximum likelihood problem, and this then leads exactly to the L2 loss, which is a very common loss for regression problems. And if you start with the multi-nully distribution, then you can end up with the cross entropy loss. So these are two very important losses, and you should definitely know how to derive them, and you should know how they are related to maximum likelihood estimations. So which distribution assumption on your data leads to that specific loss. So everybody should know that for the exam. And then we looked into a couple of additional losses, and in particular, one loss that we looked at was the hinge loss, and we could link the hinge loss actually to support vector machine training. So that was actually quite surprising because we have all this nice theory from support vector machines and so on. And we found that they can also be written up in the framework of deep learning as an optimization problem using the hinge loss. So this was a very, very interesting observation. And of course, then we need to optimize the entire problem, and there we then learned about different optimization strategies from pure gradient descent, then a couple of tricks that we use momentum, Nesterov momentum, up to Adam, how we can actually find good optimizers for our local optimization strategy. So this is then about estimating the right directions for the gradient descent, and then Adam, we have on addition also a scaling of the different dimensions. You know that some of the dimensions can have a rather large parameter space and others have a rather shallow one, that is not of such high magnitudes, and there you can then do this adaptive moment estimation where you scale the individual dimensions depending on the variation there. So very important lesson, and Adam and derived methods are very, very important for deep learning techniques today. Well, then after discussing the regression and the losses, we actually went to the one of the key ideas of deep learning, and these are the activation, convolution, and pooling. So this is our next chapter was, activation, conf, and pooling. So here we looked into the problem of, so first of all, with the activations, we've seen that many of the classical activation functions approximate this 0-1 kind of step function. So you have the sigmoid function, or you have the tangent hyperbolicus that is then from -1 to 1, but they have this non-linearity that is essentially a switch on-off. And these non-linearities are quite nice, but they cause the vanishing gradient. So we've seen because we multiply in many successive steps, so the deeper the network is, the more we multiply the respective gradients, and then we have functions that very quickly approach 0 if you access a certain part of the value domain. And this is a kind of problem, because if you multiply with something that is close to 0 a couple of times, then you essentially end up with 0. And this is called the vanishing gradient. So we don't learn anymore. And this happens in particular in the deeper layers. So in the classical approaches with the classical activations, if you build networks with 5 layers or deeper, then you typically get stuck. And the early weights, the weights in the early layers, they don't change over the training because of this instability problem. And then we've seen that there are fixes for that, which are the rectified linear units. So that's a function that is 0 on the left half space and just x on the right half space. And with these functions, we can very nicely prohibit or circumvent this vanishing gradient problems, and we can then get more stable, deeper gradients. So this was one key observation. Another important observation at this point is that you have to know about the respective gradient theory. So what we actually have here is a subgradient, because the rectified linear unit has this kink, right? It has this kink, and because it has this kink, we can't compute the gradient exactly at the position of the kink. But we've seen that if we have a subgradient, so one of the possible directions at this point, there is still a convergence proof for the entire training strategy. So it means that if you use things like ReLU, we can still find a solution. So that's mathematically all right if you are aware of how to compute such a subgradient. Then another point that we came up are the convolutions. So the convolutions allow us to tie states. So we essentially have this moving window that goes over the input domain. And the nice thing about that is, and for images, we would have like many thousands of weights if they were fully connected. But with the convolution, we can essentially boil it down to kernels. So we have much fewer parameters that we actually have to estimate. And the nice thing is the convolution can be expressed, discrete convolution can be expressed as a matrix. So we essentially can also use the backpropagation algorithm here in order to train our networks. And we see that the gradient update can also be written with essentially the same techniques as in the backpropagation algorithm. But of course, you have to incorporate that it's a circular matrix. And the next thing that we then looked at is pooling. So pooling is the idea that you successively reduce the dimensionality of the inputs. And this can be done, for example, by max pooling or by average pooling. Average pooling, you can even directly compute the derivative. For max pooling, we have to save the switches where the information came from. And we've seen that this is essentially a subgradient, again, of the optimization problem. So if we use these tricks, then we can also work with maximum operations, quantiles, and so on. So all of this is possible, and we can integrate it, and we can compute our gradient descent procedure. And this is essentially the key ingredients for the early deep learning. So convolution, pooling, these were the first popular techniques that gave the rise to deep learning and the great success in image processing. So this is a key observation here. Well, then next we looked into regularization. And draw another bubble here. Regularization. And now regularization is a technique to avoid overfitting. So that's a common problem, that you overfit, which means that you try to memorize essentially all of your input data. And first, we discussed the problem of the bias variance trade-off, which means that if we have a lot of parameters in our model, then we are essentially able to memorize the entire training data, and we get essentially a zero error on the training set. However, this may mean that the model that is created this way is not very good on unseen data, because we just overfitted on some of the examples, and therefore we are interested in models that have a good generalization ability. And this trade-off we can measure either as bias and variance. So bias means that you have a low error on your training data, and variance means that the model essentially is not varying too much in its predictions. And if we can essentially see that the error that is caused by the entire system is composed of the bias plus the variance. And we always have this trade-off that we can either reduce the bias or we can reduce the variance. But in general, for a fixed problem, for a fixed training data set, you cannot reduce both of them simultaneously. And the only way how you reduce both of them simultaneously is by including prior knowledge. So if you know how your data is distributed, if you know some properties of the problem, then you can reduce bias and variance at the same time. And this is then also called inductive bias. And we've seen then in the very end of the class that we can also reuse this in something that we call here non-operator learning. Okay, so in order to avoid overfitting, in particular if we have many parameters, we can then use regularization. And regularization is kind of also a method how we want to introduce something we know of about the properties of the system. So there are then, of course, the classical techniques. So you just work really with regularization of the loss. You can, for example, enforce sparsity, you use L1 losses and so on. So these are the classical techniques. Then we've also seen the neural network approaches like normalization. There's this batch normalization concept, and another concept that you should be aware of is dropout, where you then randomly turn off some of the neurons, and this allows us to break correlations during the training. So this is also a very classical regularization technique. Obviously, also important is that you initialize your weights right. So not just uniform random, but there's a couple of tricks like the Xavier initialization or Hay initialization that can help you to get better start configuration to work on your problem. And of course, you can reuse things that you already learned, and this then opens the domain of adaptation and transfer learning. So there you then take weights that you have learned on a different but maybe associated problem and use this as initialization, and then start the gradient updates. Also, one technique that is important for the regularization is multitask learning. So in multitask learning, you try to incorporate a loss function or construct a loss function that takes the same network, or at least some layers of that network, predict multiple different tasks, and this opens the domain of multitask learning. And you remember the rationale that we had is, if you play one instrument, it's maybe easier to learn another instrument. And this is the idea of multitask learning, that you share essentially the knowledge across tasks. Okay, after regularization, we then went on and talked about the common practices. And common practices. And here we looked into optimizers and learning rates, how to adjust them appropriately, and also the entire hyperparameters. How do I set them? Do I have to do a grid search? How about some random search? So random sampling of the hyperparameters. And we can also save essentially some points of the model and then try things like ensembling, where we then bring essentially either different models or different classifiers or different states of the training together into an ensemble. And they've seen that if you have like multiple of these classifiers, then we can construct something similar to the wisdom of the crowd, and see that if we have several weaker classifiers, we can combine them into one strong classifier. Also, another key problem is class imbalance. So this is, for example, we had this example with the credit card fraud. Most of the credit card transactions are legit and you want to allow them, but there's very, very few of them and actually try fraud, and you want to detect them. And just by their scarcity, it's very hard to predict. And if you start building a classifier that is not very good, you will start assigning many of the legit cases to the class fraudulent. So there you have to do something about your classifier, and we've seen that there's different ideas how to work with the class imbalance, that you can weight them, that you can sample them differently, and so on, in order to build a strong classifier. And also very, very important is performance evaluation. So how do I evaluate the performance? And of course, we looked into different measures of performance. And also very important is that you think about whether it actually makes a difference. Did I really improve the system, or is it just noise? Because all of these are random processes, and it could be just by chance that one result is better than another. And there we looked into ideas like significance testing that allows us to investigate the distribution of the results and then determine a probability whether they are really better or not. And this goes all into the domain of significance testing. In the next chapter, we looked into architectures. And so the architectures, I think, are very, very important in practical sense. So we looked into some of the historical ones, like LUNet, which is like the first convolutional neural network, then GoogleNet, which is like a first deep network, and it had these nice ideas of the inception blocks. And we looked also into AlexNet, which already introduced a lot of very interesting concepts, and we essentially then colored in orange which of the concepts are still around. So although the AlexNet itself is probably no longer a state-of-the-art technique, but it introduced concepts like multi-GPU and batch normalization and so on. And this is still present in many of today's models. And the GoogleNet, for example, introduced this inception block architecture, where you then have several different operations in parallel, and the network can find in which layer it wants to run which operation essentially by itself, which is a pretty cool concept. And later we then looked into the deeper architectures, and these are then like VGG and very, very common techniques, followed by a little bit of a problem that we couldn't go even more deeper. So we run into a problem with, let's say, 14, 18, 20 layers. Then we start to see worse results than with the shallower networks. And there we then learned that it's the concept of the residual connections, and the residual connections then allow us to build really deep networks. And the idea is that we just learn the difference between the input and the output, and that most of the step is essentially identity. And we take the input and add the difference on top, and this gives rise to the residual networks, which is then also a slow, gradual change from input to output. We looked into different interpretations, and I would also recommend to have a look at that. This could be also very relevant for the exam, but of course the deeper architectures are relevant, that you know these and are able to describe them. And yeah, once the ResNets came up, you can combine any of the previously looked at architectures, also with residual connections, up to very deep networks, then the dense net, then we looked into squeeze and excitation networks, which kind of also bring the concept of attention. And then if you don't know what kind of architecture you want to construct, you can also use machine learning techniques to learn architectures. And in particular, we looked into one approach that was using a recurrent neural network to construct the blueprint of the architecture, and then essentially a kind of reinforcement learning approach where you then train to build the best network for a specific problem domain. So this was learning architectures. Well, so we are already now going towards the more advanced techniques, and there we then also looked into sequence processing, and this gives then rise to the recurrent neural networks. And in the recurrent neural networks, we started with the simple Elman cell and looked into this architecture, how it's connected to itself, and that this essentially renders our backpropagation difficult because we don't know how to train it. And the key idea to be able to train it was this loop unrolling, that we put in the training sequence, the inputs, process our randomly initialized cell, and produce all of the outputs, and then we can hold essentially all of the outputs there and compute a long back propagation through the entire sequence. And that was the key idea of training recurrent neural networks. So everybody should know the Elman cell, everybody should know about loop unrolling, and everybody should know about the concept of truncated back propagation. Then next, we looked into the problem again here is vanishing gradient with the RNN, and we looked into some ideas how to alleviate that. And in particular, we looked into long short-term memory cells, the LSTMs, and into grooves. So you should all be able to know what a groove is, what an LSTM is, and you should be able to sketch them. So you don't need all of the update equations, but you should know which activations go where and how is the connection of those cells. So you should definitely know that for the exam. Good. Then in the very end, we also looked a little bit into sequence generation, how you can use a random sampling technique in order to generate sequences, and that then led up to the stage where we saw some example how to generate text from Shakespeare, and another example where people have been generating the notes actually for folk music. Next chapter was visualization and attention. So these are then techniques now to understand a bit what's happening in these black boxes. So we have these huge black boxes, and it's very hard to work with them. And in fact, it already, before understanding what's happening in the black box, there is first the communication about the black boxes, how they are constructed. And we looked in particular into how to visualize architectures. These are often these box arrow plots, where you connect nodes or entire layers. So that's very important also for science communication, that people understand what your network does. And then we also looked into the training visualization and things, for example, like TensorBoard, and how you can see then using loss curves whether you have a good training process or not. I mean, we have been using these techniques already throughout the class. I've find it important that we also talk about this, that this is actually a visualization technique. Then another problem we came up with is the problem of confounders and adversarial attacks. So a confounder, you may remember this example with these images of tanks, and that the images with tanks all were noisy and gritty and from the field. And the forest images, they were all like showing a beautiful blue sky. And there, the confounder is then that the algorithm doesn't learn tank versus no tank, but it essentially learns good weather versus bad weather. And this is, of course, something you don't want to have. So you have to be very careful when you collect your data that you don't have a confounding variable in there which allows to learn a shortcut. And these shortcuts can be not as obvious. So, for example, neural networks, convolutional neural networks, they are very good in template matching. And for example, a template match could be the noise pattern of a specific sensor. Like every camera has a very unique noise pattern. So if you take the class A, all images with one camera, and class B, all images with another camera, then it might be that your algorithm learns not to differentiate class A and B, but camera 1 and camera 2. So this is a confounder, and you have to be very careful about this. And another thing that you should be aware of are adversarial attacks. So if you know the network, then by gradient descent, you can produce an input pattern that favors a specific output pattern. And I think the most prominent example is probably the toaster sticker. So that's created from the ImageNet database, and it is an image patch that is very colorful, has some interesting shapes that may remind a little bit of a toaster, but it's for sure doesn't look like a toaster. But whenever you hold this toaster sticker into the field of view of multiple trained networks, not even the same architecture, but all convolutional neural networks and all trained on ImageNet, then the toaster sticker will map or will flip the input towards the class toaster. And of course, this is something that you don't want to have, but you should be aware of these problems of neural networks. So in order to understand these problems better, we then looked into the visualization methods. And the visualization methods in the beginning, we looked for maximally activating patches, and then you can rank which patches create the highest activations. You can also work with essentially blinding out spots. So you essentially cover different regions of the input image and then try to determine covering which region caused the highest performance loss. This also allows you to compute essentially activation maps, but it's very costly, these kind of techniques. This is why we then went on into gradient-based optimization techniques, and we looked at 3 different methods: how to propagate the gradient and how to shadow negative activations in the forward and the backward path. So we had the 3 different configurations. But the main gist of this is that you take a specific neuron, a specific layer, or a specific class, and then you back propagate into the input domain and visualize where you would have to do changes in order to create even higher activations. And this allows us then even to localize the important features in the image. So that's a very, very cool technique. And we've also seen that if we want to work on this a little more, we can use very similar techniques to then come up with something that is called inversion. And with inversion, we can essentially take a specific activation in, let's say, layer 4. And if we know that activation and the weights of the network, then we can still reconstruct the input. Although we think that, there's this deep processing and we don't know what features they're really extracting. But if I know how they're computed, then I can formulate this as a so-called inverse problem and reconstruct what has been at the input. And we've seen here, for the example of AlexNet, that even up to layer 4 or 5, we still can reconstruct the inputs fairly accurately and figure out what has been shown to this network. And this is, of course, something you should also be aware of if somebody tells you, oh yeah, let's just take layer 5 activation and then it will be anonymous. Well, no, you can still reconstruct from these activations. The last part that we talked about in this unit was then the attention mechanisms. And with attention mechanisms, you can essentially focus where the network is looking at. And we started with sequence-to-sequence translation techniques. There you can then find out which input token is related to which output token, which is very useful. And if you then formulate this, then you can essentially train a layer that is predicting this attention and does then a reweighting of the input vectors according to the current context and the current classification context. And of course, you can also do that for images, and this then allows us to find relations between specific outputs and specific inputs. And yeah, a very important paper then which we looked at is this show, attend, tell, where we can then also create, essentially link the image input to some output that is text, and then you can link parts of the image to the respective word. So that's actually a pretty cool technique. So attention mechanisms, and we talked more about that, and also attention-based translation and so on, but I won't go into too much detail at this point. Then we looked into another very popular technique, that is reinforcement learning. So this one will be also very relevant for the exam, reinforcement learning. Reinforcement learning, then we started with the entire theory. We looked into the sequential decision making. So if we have like multiple random decisions that we want to somehow make, we can formulate this in this so-called multi-armed bandit problem. And we've seen that this is something we can formulate, but we don't know about the state. And as soon as you add a state, so in the multi-armed bandit problem, we just choose the action. We choose which of the arms we're pulling. And if we want to put this into a more usable scenario, we can expand this to the so-called Markov decision process. And this is a kind of formulation where we have an agent, and the agent does some action, and this action is depending on the state of the world. So we have like the action that is determined from the state, and from the action and the state we generate a reward. So these are the three key concepts. And the reinforcement learning idea is then that we want to maximize the expected future reward, the expected future return. So this is the whole idea of reinforcement learning. And then we see that in order to be able to choose an action, we have to define something that is called a policy. Now, the policy is essentially a distribution over the actions, and we try to find policies that are good. If you know nothing about your problem, then you can, of course, do a uniform random policy. So you just pick randomly one of the actions. But this is, of course, not optimal, but it will give you a policy that you are able to play the game. And from playing the game, we then want to learn something and then create better policies. Another policy that we have seen is then the so-called greedy policy. And in the greedy policy, we just select the next action that is probably the best one. And the best one, we mean that it gives the highest future return. So in order to play greedy, we have to know something about our problem. And in order to know something about our problem, we started then introducing two functions. There was the state value function and the action value function. Now, the state value function encodes the value of that state on average. So the expected future reward that you get when you're in the state independent of the action. So this is quite cool, because if we know the value of the state, then we can, for example, pick actions in a way that they're optimal with respect to the next achieved state. So you would pick the action that brings you into the state with a higher expected future return. So if we have that, then we can see that we can estimate the value of a state by playing the game. And we can play it, for example, with a uniform random policy. So we start with uniform random and then play the game and determine the average future return for that specific state. And once we know that, we can, as decisive policy, we can then switch to a policy that will give us the maximum future return according to our uniform random state values. And the interesting thing is now that if I start playing now with this policy, now a different policy, no longer uniform random, and the greedy policy will now allow us to select states that have a higher chance of winning. And this means that we will select on average better actions than with the uniform random. So we now, by having an updated or by having knowledge about the state values and the greedy selection policy, we create a better policy. And the nice thing is we have essentially the first version of our state value function. And based on this, with the greedy action selection, we get a new policy. And with this new policy, I can now play the game again. And if I play with a new policy, I get better state values. So our state value function in all states will increase. And this is cool because if I have a better state value function and higher state values, then I know how to play this game better. So essentially with the new policy, we compute a new version of our state value function. And with this new state value function, we can then play the game again and again and again. And we see then by playing and iterating our state value function, we create every time a new policy. And this is then called policy iteration. And this is one of the basic concepts of reinforcement learning. We've then seen there's more to that, but everybody should know about the concept of policy iteration, what the state value function is, what the action value function is, what the policy is, and have a good look at this grid world example. I think it's a very good idea how to get into the line of thought of reinforcement learning. Later, we've seen when we go into the deep reinforcement learning approaches that this expected future reward is essentially a loss function. So you can take the expected future reward, interpret it as a loss function, and then plug in a neural network that predicts the state values or the action values. So you can then say, okay, our action value function or state value function, depending on how you formulate the problem, is a neural network, and we can train it. And then you compute the derivative with respect to the weights of the network, with respect to the expected future reward. And this brings us then to deep Q learning. So this is then the so-called Q function, and this is deep Q learning. And we've seen that in order to make it work in practical examples, like in AlphaGo, you have to add it with a Monte Carlo based selection of the different actions. So you can actually do a kind of Monte Carlo based pre-computation of the next couple of actions in order to have a look ahead what's going to happen in the future. And if you do that, you can essentially construct systems like AlphaGo. Yeah, so modern deep Q learning. We also had a quick look into imitation learning. So imitation learning, then you just learn the actions from somebody who shows you how to do it. So that would be only imitation learning, but this can also be done on a continuous state space. And reinforcement learning typically requires a discrete state and action space. But of course, you can discretize any continuous space and make it a reinforcement learning problem. Very well, reinforcement learning. Then we went to unsupervised learning. And you see, we don't have space for many bubbles here left. So we are approaching the end of the lecture. So unsupervised learning, you want to be aware, of course, of restricted Boltzmann machines, but they are rather historical with respect to the actual applications today. Today, much of the unsupervised learning is done using autoencoders. And in the autoencoders, yeah, you should be really aware of autoencoders. You take some input and try produce that input as the output. And then you have to add some kind of regularization to make sense out of this. And what is very commonly done is that you squeeze the state representation. So if you have like 6 inputs and you try to represent this in 3 dimensions in the center and then you blow it up again, that is the key idea of the autoencoder. So you try to compress the data somehow, and by compression and being able to reconstruct the output again, then you've probably learned something that is representative for the domain, and there is no kind of label that you need. You just need the data to train an autoencoder. And we learned about different variants. So there's the sparse autoencoder, which doesn't use a bottleneck, but it expands, but enforces a one-hot encoding in the activations, which is done by an L1 norm typically, or KL divergence on the activations, not on the weights, on the activations in this sparse layer. Then we also looked at denoising autoencoders, where you add some noise in the input and try to reconstruct the noise-free output. Then this is used to essentially neglect sources of artifact and noises. Then we've seen the stacked autoencoders, where we then stack autoencoder on autoencoder. And a very important concept is the variational autoencoder. And the variational autoencoder uses in the bottleneck essentially a distribution. So you estimate the mean and the standard deviations of the input activations. And then you sample from these in order to reconstruct the output. Now, the problem with that is that the sampling is not deterministic, and we use the reparametrization trick by adding noise as an input to the bottleneck layer to be able to have a fully backpropagatable kind of sampling process. So this is very important concept for autoencoders. The other super important unsupervised learning technique are generative adversarial networks, GANs. And the idea here is that you have a generator, and the generator tries to predict something that looks like the input data, and it's never seen actually the input data, but instead it gets the backpropagation from a discriminator. So there's 2 networks: the generator that creates something from, let's say, a noisy input, it creates images, and the discriminator just looks at the output of the generator and the true samples and says, okay, this is a generated image or this is a true image. Now, the key idea is that you backpropagate through the discriminator in order to update the generator, and this way you are able to learn something that generates realistic outputs. And these are the generative adversarial networks, and they became extremely popular. Then they have been expanded in several stages. There is the conditional generative adversarial network, the conditional GAN, which then takes an additional conditioning vector in order to enforce certain properties. Let's say you're generating faces, when you can condition them with male, female, with beard, no beard, with glasses, no glasses, and you have this conditioning vector in order to steer the output of the generation. And this can go even further, that you combine 2 conditional GANs into a so-called cycle GAN. And the cycle GAN takes domain A images and translates it to the domain B, and you take domain B images and translate them back to domain A. So both of them are conditional GANs, but you couple them with a so-called cycle loss, meaning that if I take an image from domain A, translate it to B, and translate it back to A, it should produce exactly the same output. So whatever you put in after the cycle, it should look like the same. And of course, this holds for the other side. If you start with B, convert it to A, go back to B, it should still be the same input. So this is the cycle consistency, and this is a very popular technique. It allows you to translate from one domain to another domain without having matched images. And yeah, examples are that you can translate horses to zebras and zebras to horses, or that you can also translate between different artists, that you can convert Monet to Picasso and so on. So this can be done with so-called cycle GANs. And then we looked into a couple of advanced GAN methods, like these unrolling techniques, and because there's this problem of the mode collapse. And the mode collapse means that your GAN just starts producing always the same output because it happened to guess essentially something which is very, very close to one of the samples in the training data. And this will make it very, very hard for the discriminator to differentiate the two. And if you then unroll and try off some of the advanced GAN methods, you can make the training more stable. Okay, then we went on to segmentation and object detection. So segmentation and object detection. And in segmentation and object detection, we went through the basics. What is segmentation? What is object detection? And what is classification? Classification, we assign one label to the entire image. In segmentation, we do pixel-wise identify a certain class. And in object detection, we are interested in bounding boxes. And then there's also instance segmentation, which essentially is both of the worlds. We want to know if there is multiple cats in the image. We want to know which of the pixels belong to cat A and which of the pixels to cat B, C, D, E. So this is the combined idea. We then started off with the segmentation. We looked into skip connections, and everybody of you should know UNet and how UNet works. So this is a key technology that you should be aware of. This is how you do segmentation. We talked about it a little more, but UNet is the key network that you want to be able to describe here. And then we went on to the object detection, and we had this family of regional CNNs. And here we looked essentially into how to create this object detection. We thought of first of this idea of a sliding window, but then we've seen that sliding window will be very slow because we have to look at all possible combinations. And then we found that it would be better to summarize the regions and then find out where the interesting regions are and then classifying them. In the first instance, we still needed superpixels in order to find those regions, which is kind of suboptimal. So we then and only had a CNN for the different region candidates, so this cannot be trained end to end. Then we found that it might be interesting to essentially do a multi-scale processing. This gives us these pyramid of scales, and then we apply our CNN on all the pyramid scales. And in the last step, we incorporated additionally a kind of regression that takes the input image, predicts possible regions of interest, and then of each regions of interest, we run a CNN for essentially classifying what's in this bounding box. So we have a bounding box prediction step, and then a second step that assigns a class. And these are like faster RCNN state-of-the-art techniques for object detection. Now, all of these have this two-step approach where you first localize the bounding boxes and then do the classification, although faster RCNN is actually fully differentiable, so you can train it end-to-end. You may want to have a different approach, and one key technique there when the single-shot detectors is YOLO, and YOLO then essentially did this in parallel. So it had the parallel bounding box detection and the parallel classification of the different input squares. So it subdivides the inputs into different regions that are on a regular grid. And on each of these regions, you do a bounding box regression, and on each of these regions, you do a classification. And then you have the bounding boxes. You have to take the ones that have the highest weights and not too much overlap. And for these bounding boxes, you then overlay them with the original input grid and do essentially a weighted average of the class decision to very quickly then be able to do the actual classification of this bounding box. So this turns out to be very fast. YOLO is essentially a real-time system, and we've already seen that in the very beginning with this James Bond movie, how powerful it is. Well, another one is RetinaNet. This is then using this additional pyramid scaling and this multi-resolution learning, which is also a single-shot detector. Now, a last topic we talked about is the combination of segmentation and the actual object detection, which then gives rise to the instant segmentation. And there we very coarsely looked in how we can essentially formulate this in a multitask problem where we have the actual object detection plus the segmentation losses, and how we can construct this to a method that is used for instant segmentation. Okay, good. And then we went on to weekly and self-supervised learning, and the actual contents of the exam will be the ones that I'm listing here. But on top, we had a couple of bonus chapters because I think you should know about them. Weekly supervised learning and self-supervised learning is how to create losses for very weak labels. And weekly supervised learning, you take bounding boxes and try to refine them to segmentation, or you take image-wise labels and try to create bounding boxes, or you go from 2D to 3D annotations. In self-supervised learning, you're interested in constructing interesting losses where you don't need annotations, so you can try to predict the future, you can try to predict missing patches, you can try to predict color, and this then gives rise to the combination with contrastive losses. And contrastive losses are essentially, does this do two samples belong to the same class or not? And this is also a whole family of losses that can then be generated in this way. The next chapter was graph deep learning, and graph deep learning, I think, is a very important technique. It became incredibly popular over the last few years because it allows you to do deep learning on graphs, and we had a quick idea how we could actually have graphs and how to define convolutions on graphs and what is a Fourier transform of a graph and so on. And we shortly described that in 2 videos, and I think they're quite worthwhile watching, although they're not part of the exam. And the last topic, which is also not part of the exam, is known operator learning. And here we follow this idea where we don't reinvent the wheel, but we actually use prior knowledge and directly integrate it into networks. And this shows then that it reduces the maximum error bounds and so on. So a very interesting technology, and we can use it, for example, in combination with CT reconstruction. And maybe this could even give rise to something that is then called deep design patterns. Okay, that was a quick wrap up of our lecture, and I highlighted the different parts that are important, and all the topics we talked about. You should prepare very well for the exam because all of them will be very relevant, and of course revisit your coding tasks, that you also know how to implement things. This will also be covered in the exam, so make sure that you're aware of those. And after this short wrap up, I'd be open for questions. You can type them into the chat.